In this video, I will demonstrate 2.5 ways to construct a confidence interval for the difference in two proportions using bootstrap distributions. We'll be looking at this data set. This data was collected on a random sample of 1,200 college students who were asked if they felt they were underweight, overweight, or about right. Students also provided their gender, and here is the data broken down in a two-way table. And we want to know what is the difference in proportion of females who think they are overweight and the proportion of males who think they are overweight. So first, let's identify the population. The population is going to be the entire group of interest. It's everybody that we want to draw conclusions about. And usually when we think about the population, you can use the word all. It's going to be all of some group. In this case, if we look back at our problem here, we can see that we selected our sample from college students. So our population then would be all college students. If our population is all college students, what is our sample? The sample is the subset of the population that we actually took measurements on. So in this case, it was the 1,200 randomly selected college students that we actually talked to. Next, let's talk about our population parameter. A population parameter is a number that describes the population. And in this case, it's what we are trying to estimate. So if I look at the type of variables that were measured and the number of variables that were measured, that will help me figure out what the correct population parameter is going to be. And in this study, on each individual, we measured two things. We measured their gender, and we also measured what they felt their body image was, whether they were about right, overweight, or underweight. Gender is categorical, and so is body image. So we measured two categorical variables on each individual. Here's a little chart that it makes it really easy to identify what the appropriate parameters and statistics are. So if I look along this left-hand side, I just need to find where it says two categorical, and then it gives me all the information that I need. So in this case, the parameters that I'm going to need to define are P1 and P2. I'm going to be interested in the difference in P1 and P2. The sample statistic is going to be the difference in the sample proportions. And if I was going to do a graph of this data, then a segmented or side-by-side bar chart would be a really good choice. All right, so let's look at this then. What we want to do is estimate the difference in the proportion of females and the proportion of males who think they are overweight. My population parameter is going to be PF minus PM. And then of course I need to define what PF and PM represent. So PF is going to be the proportion of female college students who think that they are overweight. And PM is going to be the proportion of male college students who think they are overweight. And again, it can help if you think about the fact that we're not talking about just the males and females that were in this study, but we're talking about all college students. So all female college students and all male college students when we're talking about the population parameter. Next, we're going to look at the best estimate for that parameter. And the best estimate is always the sample statistic. Remember our chart? It said that the sample statistic, when I have two categorical variables, is the difference in the sample proportions. So before I can find the difference though, I need to find each individual sample proportion. So I'm going to look at females first. I need to know the proportion of females who think they are overweight. So I'm going to look along this row for females. Because I want to know the proportion of females, the total number of females is going to be my denominator, and then the numerator is going to be the number of females who thought they were overweight. So that's going to be 163 divided by 760, which is 0.214. Next, I'm going to do the same thing for the males. So I want the proportion of males who think they're overweight. So in this case, the total number of males in my survey was 440. That's going to go in my denominator. And the number of males who thought they were overweight is 72. So that goes in my numerator. And that works out to being 0.164. So my sample statistic is going to be the difference in these two proportions here. So p hat f minus p hat m equal to 0.214 minus 0.164, which equals 0.050. We have basically two methods for constructing confidence intervals using bootstrap distributions, and we're going to talk about both of those methods. And with our second method, there's actually two ways to construct that confidence interval depending on what resources you have available to you. So we're going to start by looking at the standard error method, and we want to construct a 95% confidence interval. To use the standard error method, first we're going to take a sample. Next, we're going to compute the sample statistic. So we've already done this part. We took our sample, we've computed the sample statistic, which was that best estimate of the parameter. And now we're going to use StatKey to construct a bootstrap distribution by sampling with replacement from the original sample several thousand times. StatKey is actually going to make this pretty easy for us. Once we've constructed our bootstrap distribution, then we use the standard error from the bootstrap distribution to construct a confidence interval by taking the original sample statistic plus and minus 2 times the standard error. And one reminder is that when we're constructing this confidence interval, we always want to use the original sample statistic and not the mean of the bootstrap distribution. Before we go to StatKey though, let's take a look back at how we computed our sample proportions. So the p hat f and the p hat m that we have right over here. These numbers that we used in the fractions here to find those proportions are what we're going to need to enter into StatKey when we get there. So let's write those down real quick and then we'll head over to StatKey. Here I am in StatKey, and the first thing that I need to do is figure out the right place to click. And one thing that makes it a little bit easier is if I look on this far left-hand side, remember when we looked at the number and type of variables that we had? If I can find that over here, I can just move one over and that will tell me the right place to go for my bootstrap confidence interval. So I was looking at two categorical variables. So what I want to do is a confidence interval for the difference in proportions. So I'm going to click here. And once I get this open, I'm going to need to input my data. Now, categorical data is unique or different from quantitative data anyway, because you don't need the whole data set in order to analyze it, because the whole data set can be summarized just by those numbers that went into our proportions. So if I click on Edit Data here, I'm going to enter in that data that we used to construct those sample proportions. So group 1 was my females. There was 163 females who thought they were overweight out of a total of 760 females. For the males, there was 72 males that thought they were overweight out of a total of 440. I click on OK. Notice over here in the upper right-hand corner, it gives us those sample proportions that we computed earlier, and it even gives us the difference in those proportions here. Now I'm ready to construct my bootstrap distribution. So I'm going to click this Generate 1,000 Samples button a whole bunch of times. It's usually a good idea to do several thousand times. So I've got 10,000 times here. That should be pretty good. And now I'm going to use this estimate of the standard error right here to construct my confidence interval. So I'm going to take my original sample statistic plus and minus 2 times this standard error. So if you recall, my original sample statistic, the difference in the proportion, the sample proportions of females and males who felt like they were overweight was 0.050. And my standard error that we just found using the bootstrap distribution is 0.023. So my confidence interval is going to be that original sample statistic, the 0.050 plus and minus 2 times that standard error, which is 0.023. So I have 0.050 plus and minus, and then 2 times 0.023. 2 times 0.023 is equal to 0.046. So the 0.046 is my margin of error. Now I'm going to take 0.05 minus 0.046, which is 0.004, and 0.05 plus 0.046, which gives me 0.096. So this is going to be my confidence interval. Now I'm going to write my conclusion sentence about the confidence interval. We are 95% confident that the difference in the proportion of females and males who think they are overweight is between 0.004 and 0.096. Next, let's look at how we can construct a 90% confidence interval using the percentile method. When we use the percentile method, there's kind of two ways we use the percentile method. One is if we have StatKey and we can have it generate the distribution for us and do everything inside of StatKey. And the other way is more like you might see it on an exam, where you're going to have a printout of a Bootstrap distribution and you have to do it by hand. The basic idea for using the percentile method is that we're going to try to find the cutoff values in our Bootstrap distribution such that whatever our confidence level is, so say it's 90% in this example, then we would want 90% of the dots to be right in the middle, and wherever we would have to cut off the tails to make 90% of the dots in the middle, those cutoff points become the lower and upper bounds of our confidence interval. So with StatKey, process starts out very much the same as it does when we're talking about the standard error method. We're going to take a sample, we're going to compute the sample statistic, and we're going to use StatKey to construct a Bootstrap distribution by sampling with replacement from the original sample several thousand times. Then in StatKey, we're going to click on the to tail button. Once we click that button, we're going to be able to enter our confidence level in the center box. And once we do that, the bottom boxes are going to be the lower and upper bounds of the confidence interval. So there's actually no computation involved. So let's look at doing that for this data set. So as you recall, this is where our Bootstrap distribution was when we were doing the standard error method. And now to use the percentile method, I still want to use my Bootstrap distribution. I'm just going to come right over here to the upper left-hand corner, click on this to tail button. Then I want to enter my level of confidence into this center box here. So for this one, I want it to be 90% confident. So I'm going to put 0.90 in that center box. Once I do that, then see these boxes down here? Those are my lower and upper bounds of my confidence interval. So my confidence interval goes from 0.013 to 0.089. So now I can just state my conclusion, and I would say we are 90% confident that the difference in the proportion of female and male college students who think they are overweight is between 0.013 and 0.089. Now let's look at another way to do the percentile method. If you don't have StatKey handy and instead you're just given a Bootstrap distribution. So I call this doing it by hand. So when you're just given the distribution, you're going to look at the distribution provided for you and determine the number of samples taken. Then we have to figure out how many dots will be in each tail by using the following formula. The number of dots is equal to the number of samples times 1 minus the confidence level divided by 2. Once we know how many dots are in each tail, we can start on the left, count over that many dots, and then draw a line, and wherever that line crosses the x-axis, that is the lower limit of your confidence interval. Now we're going to do the same thing from the other side, this time counting in from the right. Count over that number of dots, draw a line, wherever that line crosses the x-axis is the upper limit of your confidence interval. So here is a Bootstrap distribution. This one was based on 400 samples. And just like before, we're going to find a 90% confidence interval. So I have 400 samples to start with. Now I need to figure out how many dots. So dots is figured out by taking number of samples, which was 400, times 1 minus my confidence level, which in this case was 90%. So as a decimal, that would be 0.9, divided by 2. So working out the math there, I end up with 20 dots. So starting on the left-hand side, I'm going to count over 20 dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 dots is right here. I draw a line, and where that line crosses the x-axis is the lower limit of my confidence interval. So I can see my tick marks here at 0 and 0.02. This one looks pretty close to right in between those, so I'm going to call it 0.01. Now I'm going to do the same thing from the right side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So right here is my 20 dots. I draw a line there, and where that crosses the x-axis, I'm going to call that my upper limit. So this one doesn't look quite as centered as the other one in between the grid lines, so I'm going to call it 0.092. And as before, I'm going to go ahead and write my conclusion. So we're 90% confident that the difference in the proportion of females and males college students who think they are overweight is between 0.01 and 0.092. Now, one last question. So based on this interval, or any of the other intervals that we've calculated today, is there evidence of a difference between females and males? Well, let's think about this. If there is no difference between females and males, then the difference would be 0, right? And recall that our confidence interval tells us where all the plausible values for the difference are. So if I want to know if there's evidence of a difference, then all I have to do is look at my interval and see if 0 is a plausible value. If it's not a plausible value, then there's evidence that there's a difference. And if it is a plausible value, then there's not evidence of a difference. And in this case, we can see our interval goes from 0.01 to 0.092. 0 is not in that interval, which means that there is evidence of a difference because no difference is not plausible. Make sense? So yes, there is evidence of a difference.